Okay, so linear regression models. So I think we all are used to see something like this. Whenever you hear linear regression model, and we think that, okay, so this is y is equal beta 0 plus beta 1, x1 plus beta 2, x2 plus beta k, xk, plus some, let's call it epsilon or error or u, whatever. So this is what we're all used to see, right? And we call this model linear model. Why? Because it's linear in parameters. I don't care if it is x2 square, xk to the power of 5. I really don't care if it is square root of x1. As long as the model is linear in parameters, we call it linear model, right? And then now, so this is a statistical learning language. People use betas and thetas and things like that. In machine learning, instead of these, as you can see, these are, you can think of them as weights, right? Weight for the features, right? I have x1, let's say it's education. What is the weight for that education in the model? So we call it w1, w2, and etc. wk, right? And then this beta 0 in if the data is 2-dimension, you have only y and x, we call it intercept, but if it is multiple dimension, it's a constant, right? So in machine learning language, we're going to call this constant b, and then we're going to show the coefficients with weights. So just think of this w and b. So this is going to be a matrix, is a vector of weights. So we have weight 1, weight 2, weight 3, etc. And this is going to be a constant. Does that make sense? So we're going to rewrite this econometric model in a machine learning language, but the background, the engine, nothing is going to change. We just change the notation, right? Okay, so for this slide, I'm going to do it in two parts. Part one is going to be the machine learning approach. Part two is going to be econometrics approach. So for the econometrics approach, if you have look at the slides, it's going to be optional because we have covered it in the econometrics class, and that's not the goal. But again, it's a good refresher. You can look at the assumptions for econometrics approach and then come back to the machine learning one. So let's begin. So the linear model is an important example of parametric model. Why is it parametric? Why do you think it's parametric and non-parametric? Yep. Comments?
The function is specified?
Yeah, we make some assumption about the functional form, right? So we are assuming that the functional form is linear. So we don't let it be anything it wants, right? So we are restricting the functional form. So it's parametric. And so what do we have? We have a collection of labeled examples. So these are x's and y's. So x is, guys, remember this x is a vector. So we have x1, x2, x3, and etc. And then we have only one target variable. So these are the features. This is our target variable, right? And then the sample size is going to be n. Then again, xi is a d-dimensional feature vector. So if you have education age, the dimension is 2. If you have education age, gender, the dimension is 3, and etc. Right? So it's d-dimensional in general. And then y is our real value target. So it is real valued because we're doing regression analysis. If it was categorical, it was classification. Okay, does that make sense? So then what's the functional form? So we show it with f of wb. And when we see something like this, these are the parameters of the model, right? This is a parametric model. By the way, is there an hyperparameter here? No. So the linear model only has parameters, which is w and b. W are the weights. B is this not the slope, because if it is 3-dimensional, there's no slope. It's just that constant, right? So this f of x is going to be a linear combination of features and parameterized. It is parameterized by w and b. So this is exactly the same as if I write it with beta hat 0 plus beta hat 1 x1 plus beta hat 2 x2 and etc. Right? So I want you to think of this f of wb and x as our f hat of x. This is what we estimate, right? Usually the f of x is the true function out there is unobservable. We want to estimate it. Now we're going to estimate it with f of w and b, right? Again, w is going to be a d-dimensional vector of parameters, and b is a real number, so we can call it that constant. Is the setup clear? So this is the machine learning language. If you just Google or look at the documentation for scikit-learn, you will see people are using w and b, not betas. Okay? If you read our main textbook, which is a statistical learning, they're going to use Steve Shirani Hasty, they use beta because they're focusing on the statistical learning part, not the machine learning part. All right. So, so this is the model, and the model is going to be specified with d+1 parameters. Is that clear? Because I have d dimension and one constant, so it's going to be d+1. We need to estimate those numbers, right? So we estimate the parameters, W stars and B star, by fitting the model to training data. This is, as in econometric we talk about, calculate those beta hats, beta hat 0, beta hat 1. Here we are going to calculate the weights. Because guys, remember, if I know the weights, then we're done, right? We plug the weights to the model, the functional form is known, and then we're ready to make predictions. Okay. Although it is almost never correct, a linear model often reserved as a simple and interpretable approximation of the unknown true f of x. I think this is also straightforward, right? And when we say it's almost never correct, because we know that the relationship out there usually is going to be more complex and complicated than linear relationship, right? And we have to, again, think of, for example, when we do neural networks and deep neural networks, we are going to think of any kind of relationship available between exponential variables, right? But in linear model, we're just restricting it, and it is very simplistic. It's very naive assumption, but sometimes it works perfectly. Why we like this simple linear models? Because they're extremely useful when it comes to interpretation, right? So when you want to interpret something, these are going to be extremely useful. So they're useful conceptually and practically. Because again, sometimes guys, you need to sit in front of your clients and talk to them, and you have to say, okay, if this variable changed, that happens. So for those, if you want to talk to your clients, what happened to the money, what's going on? So you have to be able to explain what happened, right? And linear models, decision trees are really, really interpretable. Linear models are really, really interpretable. So these are the ones that, again, for interpretation, we use most often. And then linear regression models rarely overfit. So they rarely overfit because of why? Why do you think they rarely overfit? Yeah, and what can you say about the bias? The bias is going to be high or low? The bias is going to be high, right? Because on average, we're not hitting at that on that target. So for that reason, we say that the linear regression models rarely overfit, specifically when the dimension is small. When the dimension is 10, 15, there's a good chance that they're not going to overfit. So I want you. So here's a question for you. I want you to look at these three graphs, three charts, and tell me which model is linear. Which of them is linear? What do you think? Yeah, good. Which one do you think is linear? Remember, guys, going back to the first slide, what is the definition of linear model? So which one is linear? Who says this one, on the one on the left? Okay. Does everyone agree that this is a linear model? What about this one? It is a linear model. What about this one? It is a linear model. All of them are linear model, right? But just remember, the model is linear for all of them. The fit is different. So I want you to understand the difference between model and fit. So here you have a linear model, linear model, linear model. Let me actually, for the guys at home, all of them are linear model, but the fit, the first one, the fit is linear. The second one, the fit is nonlinear, and the third one, the fit is nonlinear. So the difference between the second and third one is that we are using more degree for polynomial model, right? But polynomial regression is a subset of linear models, right? Because we have x, x squared, x cubed. So these are all linear models because the model is linear in parameter. The weights are linear. Okay. So that was it. Yep.
So you're talking about the red lines, correct?
Yeah, red line.
The blue lines representing?
Blue lines are, assume there's this true model out there. So we think that this is true f of x, which is unobservable. The true relationship between your x and y, which we never know in reality. But assume that here you know that reality and you want to see which model is a better fit. So if you do polynomial, we are going to see next class, with high degree of polynomial, it's going to overfit, right? It's going to do a perfect job in train set, but it's going to do a poor job in test set. As you can see, the variance of the model is going to be high. But here, the variance of the model is going to be small, but the bias is high because the model is not capturing anything, right? The model is not capturing a true relationship between variables. So in general, linear regression model rarely overfit, but it doesn't mean that it cannot overfit. So if you tune it too much, it's going to overfit. All right. Okay, now let's focus on the heart of the model. So in linear regression, here's the heart. So our loss function. How does the machine, how the machine is learning? Basically by minimizing this loss function. Now, let's define this loss function in, and guys, you will see me when I talk about different models in this class, we're gonna see this optimization again and again. I'm gonna write a minimization or maximization depending on the model that we're working, and then I define a loss function. So this is the heart of the machine, which is learning through passing the trained data set to it, right? So the machine is minimizing some parameters by changing them. Basically, the machine is minimizing these functions by changing the parameters. So in terms of terminology, this is how we write it. We say we minimize a loss function over, so you have to read it like this, over WNB. So it says that by changing the weights and the constant, the machine is able to minimize this loss function. Okay. So if you watch that video, I think StatQuest, we were changing the line. By changing the slope and intercept, you're minimizing that loss function. So this is how it's done here, right? So what is our loss function? We are looking at the errors. I think we're all familiar with what is the definition of error, right? Y minus y hat. If you look at that regression line here, so we know what are the errors. So for example, each of these things are the errors. So we look at the y minus y hat. We squared them. Why? Because we want to make sure that the positives and negatives are not canceling out each other. And then we add them up. So if we minimize that loss function by finding the correct W star and B star, we're done. We have trained the model. Is this clear? So this is very simple. We started with simple regression model because you guys all have some understanding of the loss function of the simple regression model. And then from next class, for the next models, when I'm going to start with the loss function, so we always start from this optimization problem. Okay, then we can go ahead and replace this y hat with this definition that we had for the linear regression function. And we call this objective function, loss function, or squared. Again, we can call it squared error loss as well. People give it different names, but also cost function, they're all the same. So objective function, loss function, cost function. But usually, most of the time, people use a loss function. So guys, remember, this is the heart of the model, where the machine is learning. And what does that learning mean? Finding the optimal values for weights and B. Okay. So why quadratic loss function? Why not using absolute value or Q? So what do you think is the answer? Guys, remember, this is very subjective. I could have defined instead of, because you said, okay, you have to square it because make sure that the positive negatives don't cancel each other. I could have used absolute value. If I use absolute value, they will not cancel out each other. So what's the advantage of using quadratic models versus absolute value? Or why not cubic? Why not to the power of 4? What do you think? Do you remember we talked about that well-behaved loss function last class? If it is well-behaved, we can do gradient descent, things like that. So that's exactly what's going on, right? So the more well-behaved the loss function is, so we know that this quadratic version is more convenient. It has a well-behaved derivative. Why do I care about this one? Because at the end of the day, we want to take derivative and solve for the parameters, right? So that's important to have a well-behaved loss function. If it was absolute value, so for example, if the loss function was something like this, sum the absolute value of y minus y hat. So you know that in a very simplistic way, this is not differentiable, right? The absolute value is not differentiable. So if I'm doing gradient descent, it's going to jump around here at this point. So for example, if I go a little to the left of 0, it's going to be, the slope is going to negative. A little to the right, the slope is going to be positive. So it's not going to never find that optimal. Does that make sense? So that's one reason. Another one is that there is a closed form solution. So this is really, really important. This is the part that students are having a hard time understanding what's the difference between OLS and gradient descent. In simple regression analysis, in linear regression models, if this is a loss function, I can easily go ahead and find the optimal value for that, right? So imagine if I tell you, okay, you're minimizing this function. You can go ahead, take derivative, and then see where derivative is exactly equal to 0, right? So this means that there is a closed form solution for W star and B star here. You don't need to look around, start by some random numbers, and then search for what is the optimal value for W and B. There is a closed form solution if you have this quadratic loss function. This is important. I want to make sure that everybody understands. If there is any question, just let me know. Is it clear? Okay. And the solution to this optimization problem is W star and B star. And again, when I have W star, B star, we're done. We can now move on, make prediction, and that's literally it. So with that prediction, so what are the predictions? Y hat. Now it's time to construct some metrics, how the model is doing in the test set, right? So for example, what is R square, what is adjusted R square, and et cetera. So the reason that I wanted to spend a little time here, and I believe it's important, is because from econometrics class, remember guys, we didn't talk about loss function like this or gradient descent at all. We said there's a closed form solution, and that closed form solution, we call that engine OLS, ordinary least square. And we already know what's the answer, right? So for example, in the matrix version, so we have the vector of beta hats are x prime x inverse x prime y, right? So this is perfectly, so there's a system of equations, and there's an answer to the system of equation, right? So we call it closed form solution. But as you remember, we had to make lots of assumptions for OLS to work. One of those assumptions was there's no perfect collinearity. If there's perfect collinearity, what was the problem? No, there was no solution here, because if there's perfect collinearity, it means that we cannot solve for the system of equation. There are more unknowns than equations in the model if there's perfect collinearity. If the correlation between x1 and x2 is 100%, then we cannot solve for the beta hat. So that was the caveat of OLS. Do you remember? We have to make that assumption to make sure that there's an answer. But in machine learning, again, this is just different way of looking at a linear regression model. In machine learning, do I care about those assumptions? I can say no. Why? Because if there are multiple variables and if they're perfectly correlated, if I'm not using OLS, if I'm not relying on closed form solution, I can use gradient descent. I can start from any random number and then gradually figure out what is that W star and B star without making the assumption of no perfect correlation. Does that make sense? So you see the trade-off between the two. What's the power of machine learning versus, for example, OLS in this case? Again, for the class, most of the time, the machine learning practitioners are going to rely on OLS. And because there's very small chance that in the model there exists perfect collinearity, that's a misspecification of the model itself, and we can easily get rid of it, and we can rely on OLS. But in practice, remember, we didn't need to make those assumptions. All right.
Question.
Yep.
So can you just explain again like what that W and B stands for?
Yeah, W are just the weights. So I can write down this equation, this model, right? I can write it down like this. W1 x1 plus W2 x2 plus B. Think of it as wage is equal W1 education plus W2 age plus etc. Does that make sense? And B is the constant.
Would be our slope for
You can think of it as, but again, in more than 2 dimensions, there's no slope, right? That's partial derivative. But again, if you can make an analogy to the linear regression with a simple model, yes, that's a slope. But I think it is going to be better if you get used to the call it weights instead of slopes, right? These are the weights of the features. And it makes sense, right? So what is the weight of this feature and what is the weight of education versus weight of age? All right, so now that we made predictions, let's talk about linear regression evaluation metrics. We have R square, and I think we are all familiar with R square. What's the definition of R square? What part of the variation in my target variable is explained by the model, right? So this is the definition of R square. And as you can remember, that was SSE, sum of square explained divided by sum of square total, or 1 minus SSR divided by SSC. So this is a definition of R square, 1 minus SSR divided by SSC. What part of the variation of the Y is explained by the model, right? And but if I'm looking at the R square in the train set, what's the problem with R square? As we discussed, as you may know, that the problem of R square is that regardless of what feature you're adding to the model, the R square is going to increase no matter what, right? Because do you remember the Venn diagrams? You know, if I add more x's to the model, as long as there's correlation between that x and the y variable, R square is going to increase. So in the train set, and it's not a good thing for the train set. So how did we fix that? We look at the adjusted R square. What does that adjustment mean? We adjusted for adding explanatory variables. So we have to somehow penalize the R square if you're adding explanatory variables, right? Think of that example of, I don't know, I'm regressing wage on age, education, and etc. I can add as many features as possible, right? I can add people's eye color. I can add people's hair color. I can add people's height, whatever, right? And we know it doesn't make sense, but it is guaranteed that as long as I'm adding something to the model, the R square is going to increase. So we have to somehow fix it. And for R square itself, we're going to use adjusted R square. So adjusted R square is defined as what you can see here, 1 minus R square multiply something. But that something is what matters, right? There's a trade-off between adding this k, because if I add k, the R square is going to increase. But as you can see, the denominator is going to decrease. And it has a negative effect on the adjusted R square. So there's a trade-off. When you're adding an explanatory variable, it is going to increase R square, but it's going to increase k as well, which is going to decrease the adjusted R square. So for that reason, we have to work guys remember, in the train set, we have to work with the adjusted R square, right? What are the other metrics? So we can look at the MAE, mean absolute error. So basically, we are looking at the absolute errors, take the average mean squared error. We're all familiar with this. This is how we define our loss function. And RMSE, we take the square root of MSE. Why we do that? Because the unit of RMSE makes sense. The unit of MSE doesn't make sense. So if my target variable is $, what is the unit of MSE? $to the power of 2, $2. It's nonsense. If I want to make sense out of it, I take square root, so now the unit is $, right? So we're going to work with RMSE for our regression analysis a lot. So this is a to-go metric for evaluating the model. The way that we adjusted the R square with what we call it adjusted R square, there are ways to fix this one as well. So these are, oops. Okay. So these are, I think you haven't seen this before, what we call AIC, BIC. This is Akaike information criteria and Bayesian information criteria. These are just fancy names. What you're doing is that at the end of the day, we are penalizing our metric by adding more feature to the model. As you can see, if in these two equations, and don't worry about this log likelihood. So this is the maximum likelihood. We're going to talk about it in logistic regression. For now, I just want you to abstract from all this AIC, BIC, because we're not going to look at it in machine learning. And there's a reason for that. I'll talk about it. Not in machine learning in general, for linear models. When I teach you the MLE, maximum likelihood estimator, we're going to talk about this loss function. And then you will see what basically it does. But what I want you to focus is that look at the big picture. What are we doing? What is AIC and BIC is doing? AIC and BIC are penalizing your statistic by adding more explanatory variable, by adding more features. As you can see, if I add more dimension to the model, K is going to increase. If K increase, AIC increase, and BIC also increase. And this is bad because the lower AIC and lower BIC is better. The higher adjusted R square is better, the lower AIC and the lower BIC. Think of AIC and BIC of two different methods, other evaluation metrics, which has adjusted for the adjusted version for adding more features to the model. Does that make sense? Okay. Again, just focus on the big picture now. We're going to revisit this log likelihood function. It makes more sense. But what I'm trying to say that in linear regression, you really don't need to be worried about this. Okay, this is a very subtle point. I want you to pay attention in machine learning. This is the case in econometrics if you're looking at the train set. You want to see how your model is doing in the train set, right? So for that reason, you say, okay, in the train set, I can add enough explanatory variables to the point that R square is almost 100% or MSE error is almost 0. But if you do that, what will happen to prediction in the test set? It's going to be way worse, right? So just think of it this way, guys. Imagine I have a model like this. So I can go ahead and make sure and tune, just tune the parameters and hyperparameters of the model, make it a lot more complex in a way that the R square is almost 100%, right? But this is the R square in the train set. If I calculate the R square in the test set, let's say these are the observations in the test set, it's going to do a very poor job. So the R square in the test set is going to be very small. Does everyone see that? This is important. And because in machine learning, we do care about the R square in the test set, so we know that the model never goes to that way, to that direction. Because you always want to look at the R square of the test set, so you're not going to add features to the model to the point that R square of train is 1, because you know that the R square test is hurting. Okay, so for that reason, we don't need to be worried about adjusting these metrics. So namely R square and RMSE. You don't need to be worried about that, because in machine learning, we look at the performance of the model in the test set. It is automatically taken care of. This is a subtle point. Just let me know if there's confusion. Okay, and just one step further, because I know that this test, the test set in machine learning is not necessarily observable, we're going to estimate these numbers, R square in the test set, MSE in the test set, RMSE in the test set, by doing cross-validation. So that's the last step. So in Python, we're going to see that at the end of the day, I do care about the R square of the test set. But I have to estimate this R square of the test set. How do I do that? By using cross-validation. And you're going to see how numbers are close. So we're going to call it R square of cross-validation, RMSE of cross-validation, and etc. These are the numbers that we care in machine learning, right? And it's going to automatically take care of this adjustment for you. This is really, really important. I hope that you understood why it automatically takes care of that part. Because if you overfit the model, yes, R square in the train set is going to do a perfect job, but in the test set is going to do a poor job. So you never go to that direction. Are we good? All right. Okay, so the second part is the econometric approach. I'm going to skip, and what are we doing in the econometric approach? We start with a bunch of assumptions, right? In order to use the OLS, we have to make sure that these assumptions are valid. So this is from the econometric course, right? We had 6 assumptions. We relaxed the last one, which was the normality, by having a large sample size, right? So the OLS can still does the job if none of these assumptions are valid. But what's the problem? You cannot rely on the coefficients. Do you remember we had this conversation? You cannot rely on the t-stat. You cannot rely on the f-stat. So you cannot say that your story that you're telling is statistically significant or not, right? But in machine learning, if you don't care about that part, okay, you can skip and use OLS without checking any of these assumptions. Does that make sense? And what are the assumptions? Okay, the first one is linearity in parameters. The second one, random sampling, no perfect collinearity, zero conditional. This was crucial for ceteris paribus interpretation, right? So we need to make sure that on average, the unobserved factors on average has nothing to do with your feature space. And then finally, the last one was homoscedasticity. Because if it is heteroscedastic, we know that we cannot rely on the distribution for the f-test and things like that. Okay. So again, this is just a refresher. I want you to look at these assumptions. I took this from the econometric course. And then what's the message here? So this is the question of the day. So you proceed from a false assumption. I have no ego to bruise. So who is this? Not the guy. I'm thinking of. Who is this guy? If you want to replace it with OLS versus machine learning, which one is that? OLS is saying this sentence, or machine learning is saying this sentence. You proceed from a false assumption. I have no ego to bruise. Let me put it the other way. At the end of the day, should we care about all the assumptions in the econometric class in order to use the OLS? If yes or no, if yes, why? If no, why? What's your thought? Yep.
I think if we're focused on prediction primarily with machine learning, as opposed to establishing some type of relationship like in econometrics, then it would be okay to ignore the assumptions, right?
Yeah, exactly. So Tristan, right? So as Tristan said, yeah, if at the end of the day you only want to care about the predictions, you can relax those assumptions and say that okay, most probably they're not valid. But what I'm trying to say here is that if you're given a data set that you can see all the assumptions are there, you have a model and you can check that all the assumptions are there. The model is homoscedastic. You can see there's no endogeneity, things like that. If that's the case, which by the way is rarely the case in reality, then you don't need to use machine learning. OLS is going to be blue, best linear unbiased estimator. So don't bother and use machine learning because the OLS is going to do a perfect job. There's closed form solution for your variables that you're looking for. But the problem is that in reality, these assumptions are mostly violated. Does that make sense? Okay, so let me stop here and I'm gonna stop sharing and let's go to the Python part. So for Python part, let me see. So this is the HTML version. Let me look at the notebook version. So so if you just update your GitHub, okay, let me see, where's my GitHub on this computer? I think it's on document. Yeah, document GitHub. So I go to document, then GitHub, oops, yeah, this course, classes, class 6. Okay, let's open up this linear regression notebook. Okay. I'm gonna have an HTML version of it open somewhere. So this is the HTML version, which I already saved. And this is the notebook version. The reason that I want to have this one open because we're going to go back and forth between the data. I don't want to scroll up and down. So just visually, it's going to be easier to follow. All right. So linear regression. And guys, this is machine learning course. So we are going to focus on the machine learning approach only. So we're not going to talk about the interpretability of the variables or the t-stats, p-values, things like that. Okay. And this is what most machine learning practitioners are going to do. But I want you to know the difference. If you go to industry and work someday and work with the linear regression model, be aware of what you're doing. Most probably the underlying assumption of OLS are violated. So don't jump into making conclusion, interpret things, right? You will be excited. You have a high R score even in the test set and you're excited to interpret things. But remember, the OLS assumptions are violated, okay? Is it going to work? Yes. If you want to make a prediction, yes. But if you want to tell a story, don't do that. It doesn't make sense. Okay. And this is something that I have seen by experience that many people have no idea what they're talking about. So they just run a linear regression model, and then they think, okay, here's the story. Those are fake significancy that you're getting if the assumptions are violated. All right. Okay. So what is this sign here? Run. Okay. So let's import the libraries first. NumPy, Pandas, Matplotlib, Seaborn. So these are for visualization, even though we don't have much visualization for the linear regression because it's more than 2 dimensions, multiple regression model. So there are 2 packages that may be new to you guys. So the first one is scikit-learn, and the second one is stats model. Is the font size good? The color size, brightness? Okay. So the scikit-learn, again, this is the package, our go-to package for machine learning. So it covers all the models that we do in the class in Python. And so and most practitioners out there are going to work with scikit-learn. And we're going to use for the machine learning approach of linear regression models. But if you want to do a econometric approach, it's going to be a lot easier to work with the stats model. I'm going to show you both. But again, I'm quite confident that when you do these things in practice, in industry, people are using scikit-learn. Or if it is, I don't know, if it is R, they're doing H2O. If it is Python, they're doing scikit-learn. Okay, so let's run this cell. Make sure that we import this. And guys, because the reason that we're using subclass in a package, so scikit-learn is a package and linear models is a class of models. The reason that we don't import the entire scikit-learn is because it's huge. package is huge. For each Python, for each notebook, we're gonna import only the ones that we're gonna work with the model, right? So if it is linear model, we just import the linear model. If it is random forest, we're gonna import the random forest. I could have just done something like this. Just erase this part and import the entire scikit-learn as SK maybe. And then, but remember, it's going to be huge. It's going to take a lot of memory of your computer. These are, so from this scikit-learn linear model, we're going to import a class, which is called linear regression. So this is a method that means that you can, out of this linear regression, you can train the model using that linear regression model, right? Okay, now let's set the random state equal to 1000. So what is this random state? The random state, what we do in Python usually, sometimes we have to generate some random numbers, especially when it comes to splitting the data. Let's say I have 100 observation, I want to split it to 80 versus 20, right? If you want to make sure that your answers are exactly the same as mine, you have to use the random state is equal to 1000. So if you do 1000 on your computer, then the seed on your computer is going to be exactly the same as mine. You will see exact same number. But if you use different number, let's say 1, 2, 3, or if you don't use anything, it's going to be randomly assigned, right? Your numbers are going to be different than mine. So it's no big deal. So for the homework questions, I think there's a good chance that your answers are going to be different from the answer key because of many reasons. You know, we start from different random numbers, even if the random numbers are the same. For different reasons, there's a good chance that our numbers are going to be different. So usually for the homeworks, I'm going to say that, okay, my model, the R-score, adjusted R-score, RMSE of the model was 100. See if you can beat me or not. This is the way that we do it for the machine learning homeworks, right? And most of the time you can, because I go with the simplest model and you think way better than me. So usually students historically has beaten me when it comes to homework. So no, you can do it too. All right, so that's why we define the random state. So again, if you want to see exact numbers as mine in this notebooks, just put it to 1000. Now let's import Boston. We're going to work with Boston dataset. As the name suggests, this is some information from the properties in Boston. And this is one of the famous data sets which comes with the scikit-learn package. So do you remember in R, we had some built-in data sets? So these are the built-in data sets that come with scikit-learn package, right? So how can I access them? So I say from scikit-learn data sets, import load Boston. This is just the name of a data set, right? And so then you import that, and now you can load that. I'm gonna make a new data frame, call it Boston. It's not data frame yet, right? And then if I do load Boston, open close parentheses, it's going to save whatever it's in the package, in that data set in the package, let's say to an object called Boston. Is this clear so far? Now let's see what is inside that Boston. If I just go ahead and see what's inside, it's going to be very ugly, right? So it seems that there's an array of feature variables, and there's target variables. This is our Y variable, right? And then there is some feature names. So this is ugly. This is not necessarily the cleanest version. And then I'm going to see what's available in that data set, in that object that you're saying. It's a dir Boston. If you do dir, basically tell you that, okay, what can you get out of this data set? You can call it description. You can call data. These are the X values. You can call feature names. You can call file name, and you can call the target, right? So for example, if I look at the description, if I print the description, so this is, oops, I think I didn't run this line. So this is a description for the Boston dataset, right? So as you can see, there are 506 observations, there are 13 features, and then one predictive, there's one categorical predictive. No, sorry, this is 13 numeric and categorical, and then one predictive. And these are the name of the variables, right? So let's see, what are they? At the end of the day, we have CRIM. So this is per capita crime rate. We have ZN, proportion of residential land zoned for lots over 25,000 square feet. Then we have, probably it's industrial, proportion of non-retail business. We have CHAS or CHAS, whatever, Charles River dummy variable. If it is 1, it's 1 if track bounds river, otherwise it's 0. NOx, nitroxide concentration. And then we have number of rooms, right? Per dwelling. We have age, so this is the older the property it is. So if it is built prior to 1940, we have this. This is the weighted distance to 5 Boston Employment Center. We have RAD, index of accessibility to radial highways. This is a bad thing, I guess, for residential properties, right? If it is closer to radial highways. Then tax, of course, it's a bad thing for the price of a house. Then pupil teacher ratio, again, the higher this number, maybe the worse it is, because the school zone matters. Then B is a standardized version of the black proportion. And I assume that they wanted to standardize it because maybe this is the average proportion of white. So they say that, okay, black minus white, they wanted to make sure that not to be negative, so just square them and then normalize it by multiplying by 1,000. At the end of the day, what you care is that this is some sort of proportion for blacks, right? And then LStat, or LStat, this is a percentage of lower status of the population. So the higher this number, what do you think is going to happen to the price of house? The higher the LStat. Down, right? So we'll see if it's to that direction or not. And then finally, this is our target variable, median value of owner-occupied home, and the unit is in $1,000. Okay, so what do we want to do? We want to do a simple regression analysis, regressing this, let's call it price, on everything else. Sounds straightforward? Okay, so this is what we're going to do. At the end of the day, we want to see what impacts the price of a house. But guys, remember, this is machine learning, so most probably we don't care about the coefficients themselves, but we want to see how the model is doing a good job in the test set or not, right? Okay, so again, this is hard to work with this, what I just called Boston object. So we're gonna clean it out. So let's see how we can clean it out. So first of all, let's look at the feature name. So these are the name of the features, and then this is the data. The type of the data is going to be NumPy array. So your first job, and we're going to work with one or more of these built-in data sets from now on, but I decided to put it here because you have a template for yourself. But if you want to work with other data sets from scikit-learn, you know how to do that, right? So this is your first job. You have to make a clean data frame out of it. Let's make a data frame. What is the data? Boston.data. Remember what were the features we had? We had data, we had feature names, we had target, and etc. Right? So this is Boston data, columns, Boston feature names, and then now I'm going to add the target variable, price, which is Boston.target. Now, if I look at the head of Boston, this is what you guys are used to see. This is my clean data frame, right? This is my target variable, price, and these are a bunch of features. Are we good?
So you just changed the name?
Yeah, just change the name from, I think it was median price to price, and then didn't change the features. Okay. So the model starts from here. And I think there is one homework that I want you to do the same thing to the Boston, so you can use this notebook. In terms of EDA, it's going to be pretty straightforward. So if I look at the unique numbers in that data frame, because the samples, because the number of features was only 13, I didn't write that for loop as you did for the New York property, because there's only 13 of them. I can see them all here. If it is 100 of them, maybe you can do it in a for loop. And so it seems to me that all of them should be numerical except this chas. So this is dummy variable. If it is one close to that river, otherwise not. But here I'm not gonna, well, let me see. We can do it or not, because here it really doesn't matter, because this variable can only take 0, 1. So if it is only 0, 1, it really doesn't matter if you make it a factor, a categorical variable or not, right? But if it is 3 classes, you have to make it categorical. And let's look at the information. Good news is that all the variables are non-null, so this is really good news. Then we can value count the RAD if you're curious to see what's inside. Again, this should be numerical, and that's totally fine. And then this is our close to river or not. So it's not proportional. It's 471 of them are 0, 35, or 1. Okay, we can look at the description, so using the describe function. And guys, I assume that you guys are expert in terms of EDA by now, so I'll just move on. But the one that I personally will focus is always the target variable. If you look at the target variable, so look at mean. Mean is 22.5. What is median? Median is 21. So not surprisingly, it's going to be right skewed, right? So the price of a house is going to be right skewed. So right now, I know that if I use log transformation, it's going to do a better job. Okay, but let's say we don't want to make any assumption. Let's move on with the machine learning approach, right? Let's keep everything mechanical. This is not necessarily a good approach, right? I just want you to understand the differences, right? If you can add some art into machine learning as well, some intuition is going to be work a lot better than simply close your eyes and say that just throw the data into a machine learning model, see what's the output. So what I'm trying to say is that right now I know if I do a log transformation, the output is going to be better. Okay, but let's move on. Let's keep it simple to reprise, and I leave it as an exercise to you. Just redo the entire thing by doing log transformation of the price of your target variable. Okay. So yeah, we already answered this one. We can quickly look at the correlation metrics. And so again, the one that I care is what's the relationship between price and the features. Not surprisingly, the price is going to go down with higher crime, go up with this ZN and then industrial. So this is residential, industrial, again, negative, makes sense. Close to that river or not, I don't know if it's something good. I haven't been to Boston. Definitely this makes sense. The higher the oxide concentration, the lower the price. It seems that it makes sense, right? At least intuitively, the older, the cheaper, and etc. And so this one, LSTAT, as you guys guess, look at that, the correlation is really big. So the lower status, what was the name of it? Lower, what was the LSTAT? Oops, sorry. Okay, it's percentage of lower status of the population. Makes sense, you know, if it is in one of those slums, so most probably the house is cheaper, right? Okay, so this is what you should infer from this correlation matrix. And then for fun, we can do some pair plot. And the reason that I pick only these ones, because these ones were the one that has higher correlation. You can pick whatever you want. And we can look at the pair plots. And the one that I wanted to focus is here. Look at the price versus LSTAT. It seems that if you want to do a fit only using LSTAT as an explanatory variable or the feature, you should use polynomial regression. Does everyone see that? Because the fit is not linear, definitely the fit. A linear fit is not going to do a good job. As you can see, a nonlinear fit is going to do a better job. So namely, polynomial regression is going to do a better job if you want to only look at LSTAT versus price. This is something that you do for your homework. Okay? You're going to look at LSTAT versus price. And then I want you to fit a polynomial regression model to that. Okay, and so this is, we have a bigger version of it. So obviously a linear fit is not going to do a good job, so we have to do nonlinear. And you will figure out if it is polynomial degree 2, 3, and etc. So next class, I will teach you how to do it in Python. All right, now let's start by splitting the data into train and test, right? So, and this terminology is very, very standard. I want you to just to state this, the name of that we pick for the y and x. So for the target variable, we use little y. For features, we're going to use capital X. Okay, just this is very standard. I want you to get used to it. And so what is your target variable? From the data frame, the price is your target variable. What are your features? So again, there are two ways to do that. I could have written something like this, df, and just list all the names. I have 13 of them. Or I could be a little more smart and do it this way. I'm going to say drop price from the columns, but without in place is equal to true. Because if I in place equal to true, it's going to rewrite the entire data set, right? So it's going to temporarily get rid of the price from the data set and just now save everything to the x for me. Are you following? Okay, so this should be straightforward. Just let me or the TAs know if you have any specific questions from the code. Then look at that. We're from scikit-learn, model selection, we're importing train test split. So if I import the train test split, now let me actually show you the, it's not working. My keyboard, the shortcut key is not working. I don't know why the hell. Oh, because this, oh, sorry. Is it? No, this is not the HTML. I don't know why that contextual help is not showing up here. No, not you. So, no. Oh, I don't know how to work without the shortcut key. How can I add a contextual help without doing Control-I? Okay, it's not working. I just wanted to show you that what is each of these functions is doing. So not you, maybe. No, open, no. Oh, because this is, somehow this is notebook. Okay, I wanted to open it as a Jupyter lab. That's why the control I doesn't work. Anyways, so did I open a notebook? So why did you not correct? It's fine, you know, notebook and Jupyter labs. So that's why the control I is not working. Okay, anyways. Sorry. Hopefully, when you do control I, you see that documentation. Yeah, that. Let me actually quickly do that because it is something we need. And it really doesn't matter how many of them you have open, as long as your data set is small and model is tiny, you can do it. So Jupyter Lab. Okay. So I'll go to document, GitHub. 2021 classes 6. There you go. So let me quickly run through the first lines. Okay, we are here. Now the control I works. Yes, sweet. Bless you. Okay, so you're importing this train test split function, right? When I click on this train test split, see what are the inputs. So it says that tell me what is the test size, what is the train size, and the output is going to be 4 things. We call them X train, X test, Y train, Y test, right? And I separate them using a comma. So the output of this function is going to be 4 new data sets, and we can save them, give them 4 different names, right? So the first output is X train, the second output is X test, the third one Y train, the fourth one Y test. Why is it like that? Because the author of the package decided to do it this way, right? Whenever you are confused, just click on the function and then scroll down. You'll see there are some examples here. See, for example, see, this is the example. So this is how you should know. The first one is X train, X test, X, Y train, Y test. Okay. All right. So what are we doing here? We are taking these X and Y. This is the entire data, right? So these are the features. This is the target variable. And we're splitting them. You're splitting them into train set and test set. Remember, we don't do validation set, right? So let's split them. So pass the features, pass the target variable. What is your test size? I can 20% test size. So 20% test size means 80% train size. I could have written train size equal to 0.8. Exactly the same thing, right? And then random state, this is 1000 that we define up there, right? Now, if I go ahead and look at, so this is just for if you want to check that everything is done correctly. I'm just saying, what is the size of train divided by entire thing? It should be around 80%, right? If the test train split is being done correctly. Now I can look at the head of the train set. See, so this is, so this function is going to divide your entire data set to 80% train, 20% test, and this is completely done randomly. So the 300th observation is coming first, and etc. Right? So we are shuffling the data. Remember, we are shuffling the data, and then we're calling 80% of his test train set, 20% of his test set. We train the model using the train set. We test the model on the test set. Okay. Now let's do linear regression using scikit-learn. And generally, guys, the application of machine learning in Python is 4 lines of code, and you will see it here. Just 4 or 5 lines of code. It's really, the application is pretty straightforward. Okay. So usually, and the steps are very the same. So usually, you have to define a model. I call it regression model. You can call it anything. And you pass this linear regression. So you say that there's an object. That object is linear regression. Okay. Then you use that object. Out of that object, you can use the fit. Let's see, what do we have? So, for example, now I have this object. Guys, I know if this is the first time that you're saying it, it's going to seem a little strange, but you will get used to it because the steps is going to be repeated again and again and again. For every model, we do the same thing. Call the name of a function, save it as a model, and then use fit, predict, and that's it. Okay. So we can, what can we do? We can say, this is the model that this is the object that you call it linear regression, right? So if I press tab, so I can fit intercept, I can make predictions, I can look at the score. Does that make sense? At the end of the day, if I do random forest, so I write random forest here, and I can fit, predict. If I do SVM, I do SVM here, fit, predict, right? So the steps are very, very straightforward. Okay, so let's go ahead and fit the model. We fit using the train. So this is where the training is happening, when the machine is learning. And behind the scene, that loss function is being minimized, and W and B stars are being calculated, and it's done. So when I run this line, that part is done. Now the W star has been calculated, and the B star has been calculated, right? I can look at, and then when the model is trained, I want to make some predictions on the test set. Is everybody following? Right? So I'm going to make predictions on the test set. So I say, this is the model, make predictions on the test set. I call it y hat, and then I make a nice data frame with this new prediction. So what is the data frame? I want to see the actuals versus predictions. And I can look at, calculate the difference, call it residual. So what is this data frame? I have actuals, predictions, residuals. So this means that in the test set, the 483rd observation was $21.8 thousand. The prediction was 21.28, right? How off we are? Y minus y hat, 0.51. Is everyone following? Okay. Now that we have predictions, we're done, right? So the machine learning has done its job. So we look at the prediction in the test set. Now let's see how we did. Look at the evaluation metrics, R-square, adjusted R-square, and things like that, right? So of course, we can look at the coefficients too. So if you want to look at the coefficients, so just call the coefficients. Or if you want to see what's the intercept. As you can see, the scikit-learn package is not designed for interpretability. So even when you call something like that, the coefficient, it doesn't tell you what are the coefficients. You have to manually construct those things, right? So you have to manually construct the data frame. And so this is what I'm doing here. Okay, let's have a regression summary. In the data frame, the name are the features. So for example, here are the name of the features. And then what are the, so these are the names. The column name is, let's call it coefficients or features, whatever. And then I'm going to add the coefficients to that data frame. So at the end of the day, you will see something like this. Is everybody following what's happening here? This should be straightforward. Okay. Then we get to the evaluation. Let's see how far. Okay, we have a couple of minutes. Let me go over the first couple of cells, and then we leave the rest to the next class. Because again, we are going to continue the polynomial regression. Next class is going to be shorter, the theory part, because it's not that complicated. Okay, so let me actually give you the big picture. I don't go over the details. We train the model using the train sets. Now the goal is to test it over the test set, right? So it means that don't get lost in the technical, on the details of how to code these things. At the end of the day, you're going to use a template, you're going to memorize things, you're going to copy from other people's code on the internet, right? Don't get lost in how for example, this is done or that. Get the big picture. So for example, we can calculate the R-square in the train set. So the R-square in the train set is going to be 75%. We can also calculate the R-square in the test set, which is 69%, right? So not surprisingly, in the test set, the model is doing a worse job than the train set. So this is not surprising at all. We can calculate the adjusted R-score for adjust.
Why is it not surprising at all?
Because your model is going, in the train set, the model has seen the data, but you're testing it in something that the model hasn't seen. Okay, so it's always the case. The performance in the test set is always worse than, or at best is equal, but it's always worse than the train set. Okay, good question. If you want to do adjusted R-square, again, it's not even defined in scikit-learn package. You have to do it manually. Okay, so in scikit, why? Because literally we don't need it. In machine learning, we are going to look at these evaluation metrics in the test set. So that's why even it's not defined something like adjusted R-square in scikit-learn package. Do you understand what's going on? Okay. So again, for your own reference, if you wanted, so for example, I define a function myself. I call it adjusted R-square, and if you can calculate the adjusted R-square in the test set as well, right? So in the train set, 74%, in the test set, 65%. Then MSE, RMSE, we can look at these numbers as well, but what's the goal? The goal is to estimate the MSE in the test set, estimate the R-square in the test set, because remember guys, the test set is not always observable, it's not always labeled, right? So let's estimate that number. And you're going to estimate that number using cross-validation. I'm going to review these things next class. You're using cross-validation, and by cross-validation, at the end of the day, you get an estimated version of that. So R-square, the estimated version the cross-validated version is 70%. Okay, so this 70% is the estimated version of the R-score in the test set. Do you remember it was close to 69? Where is it? So we tested, we estimated this number using cross-validation. And see how close it's at? Okay, and that's all we need. So when it comes to regression analysis, we need to estimate the R-score in the test set by doing cross-validation. We need to estimate the MSE of the test set by doing cross-validation. And the number that we usually, if you want to compare the models with each other, the number that we refer to is always RMSE. So the RMSE is, this is the, at the end of the day, we do care about this number. The smaller this number, the better. And you're comparing different machine learning models, right? So for example, you use the regression analysis, it was 4.7. You use another model, it's less than that. So that another model is going to do a better job. All right, so let's stop here. And then, yeah,